Okay, so we can see the effect of dark matter on within galaxies upon the rotational movement of disk stars, and we can see the influence of dark matter kind of strewn within clusters of galaxies. But is dark matter really there? Well, either dark matter really exists, and believe me, people are chasing down what dark matter looks like, or dark matter does not exist because our understanding of the universe and how gravity works is wrong. And actually, that second scenario, that we're kind of off base with regard to inferring or calculating the amount of dark matter in a galaxy or a galaxy cluster, or the amount of dark matter in our universe, that's not possible necessarily. I don't know how strong to put this, but that cannot be the case because gravity is so well known. So I mentioned folks that are chasing down dark matter, among other things. And there are a group of particle physicists, actually a network of particle physicists, that are really engaged in looking at subatomic particles. And they can use these particle colliders. And this is a very famous particle accelerator in, actually it's kind of between Switzerland and France. And it's called the Large Hadron Collider. And I've got on my playlist for this chapter some really great videos, and one of them is a young man who talks about the Large Hadron Collider, and he mentions dark matter. But anyway, so in order to understand dark matter, we're going to have to understand matter in general even more. Beyond the protons and neutrons and electrons, and they already know a lot beyond that. But so what is dark matter in our universe? Well, there's actually kind of two basic options, or it could be a combination of these two. For instance, the matter out there could be dark, underluminous, simply because it's not glowing, or I don't know. There's this group of objects called MACHOs, massive compact halo objects. For instance, a failed star wouldn't necessarily emit electromagnetic radiation if it had cooled down, and yet it would definitely have mass. It would attribute mass to a galaxy, or to the halo region of a galaxy. Okay, so MACHOs. The other option for dark matter would be a little bit more exotic or interesting, and as it turns out, actually, this WIMPs is the best bet. And what WIMPs stand for, I love how WIMPs is converse to MACHOs, the dichotomy going on there. Isn't that neat? WIMPs are not wimpy. WIMPs stand for weakly interacting massive particles. And so this would be actually something a little much more exotic, another particle or subatomic particle. And I'm going to go ahead and put up a couple links here. I'm not going to play these links, but again, these are associated with Chapter 16. This last late summer, early fall, the Large Hadron Collider, actually, I believe it was, they isolated, I guess that's the word. What they do in particle colliders, just kind of simply, is they, you saw that previous slide with a 17-mile track. They take particles and they accelerate them, and then they let these particles collide, and then they isolate and they look for what little pieces are left over, or are created from the collision, I guess I should say. So anyway, the Higgs boson particle actually has been an elusive particle, and actually can get us down the road into kind of understanding maybe what these WIMPs, weakly interacting massive particles, what gives mass to matter, that sort of thing. It is so interesting. So WIMPs, we really believe that that's probably more likely the case. But I mentioned that the dark matter that is associated with our galaxy, the dark matter that's kind of strewn throughout the universe, could actually be a combination of both MACHOs and WIMPs. For instance, I'll go ahead and kind of put up this whole slide. For instance, we do see MACHOs that can create gravitational lensing for distant objects from us. You can kind of see this is a macho that's going between us and the sun, and we can see the lensing effect. But machos don't account for, or not us and the sun, sorry, us and a star. I was like, wow, that's going within, no, in our solar system. Us and a distant star, we can see the gravitational lensing that's caused by this macho. And it happens, but there aren't enough machos out there to explain for the amount of dark matter that needs to be accounted for. Does that make sense? So WIMPs. Okay. WIMPs actually, when we get to start talking about in the next chapter about the Big Bang theory and how our universe was created, these weakly interactive massive particles really kind of begin to gel or make sense, are consistent with the Big Bang theory. And also, when we talk about, along those lines, the formation of galaxies, we're going to see that WIMPs actually kind of help facilitate that process too. Speaking of, here's a proto-galactic cloud, and the presence of WIMPs actually, we believe, can start to make this, the evolution of a proto-galactic cloud into a galaxy of stars. So just to kind of remind you, we looked at this slide before. This is looking at the Milky Way galaxy edge on. You see the halo region, those kind of pretty red, maybe globular clusters. And then our Milky Way galaxy has a fair bit of dark matter, which again we believe to be these weakly interacting massive particles. Now, the thing about weakly interacting massive particles is that they do not respond to gravity, but they exert a gravitational force. Isn't that cool? So actually what you're looking at is now these arrows are showing kind of the vectors of the movement of galaxies within our universe. And so as it turns out, regions of dark matter, these WIMPs, weakly interacting massive particles, can actually be kind of a place where galaxies kind of begin to congregate. And in the next slide, so this is kind of what we see in the overall structure of our universe. So we end up with these sort of walls of galaxies. So this is showing you these little dots, these yellow dots here now, are showing you galaxies within our universe. And specifically, you can kind of start to see kind of some voids, what we call voids. Okay, so our galaxy, Milky Way galaxy, is over here, looking farther and farther. And one of the things that this slide kind of highlights is that out here, it's not that there are necessarily fewer galaxies. Each yellow dot is a galaxy of stars. It's just that it is more difficult to gather information or to see these galaxies out here. So you see these kind of great walls. We have several of them. This would be where these dark matter, these weakly interactive massive particles, are exerting a gravitational force and kind of congregating these clusters of galaxies into one spot. So we have a CFA Great Wall, we have a another Great Wall, Sloan Great Wall. Okay. So one of the things about kind of weakly interactive massive particles, I mentioned they can kind of help explain after the Big Bang how we got this unit we call a galaxy. So what you're going to look at is a series of boxes here, and each box is showing an expanding galaxy, an expanding universe, and each box is showing an expanding universe, and within that universe start to kind of see, we're going to talk in the next chapter how it cooled down, and you can start to kind of see where these galaxies kind of formed on kind of this webby looking material. When I say webby looking material, that's kind of like the walls of galaxies or galaxy clusters around voids. And so weakly interacting massive particles, the existence of them can support what we see. The universe kind of grew lumpier with time based upon the location of these WIMPs. So again, here is kind kind of isn't this a neat look at our universe now? You know, it's just a small fraction of our universe, but again, weakly interacting massive particles, excuse me, WIMPs, actually kind of, the modeling shows that these walls and voids are consistent with their presence. Just need to kind of understand more what dark matter is.